So today we will continue our discussion of ensemble methods. So last week we spoke about trees, and then we moved on to ensembles of trees, parallel ensembles of trees. We talked about random forest and bagging. And in these scenarios, we were building lots of prediction functions, lots of trees in this case, to solve the same problem. And then at the end, we would combine them in a rather simple way, just average them or do some simple kind of majority voting if they were hard classifiers. Today, we're going to talk about a different type of ensembling approach called sequential ensembles. And in a sequential ensemble, the idea is that you build a model, you build a prediction function to fit your data, and then in some sense, you see where your prediction function did poorly on your training data, and you fit a new model to correct the mistakes of the first one. And then the final prediction would be some combination of those two, typically a linear combination of those two prediction functions. But then you could go another step and see where the combination does poorly on the training data and fix those errors with a third prediction function. And you combine them. And this is a sequential ensemble because you sequentially add one more prediction function to the collection at a time, each one depending on what happened before, because it tries to make things better in each step. So it's not really parallelizable in the same way that parallel ensembles are parallelizable. So the traditional starting point to talk about sequential ensembles is a method called Adaboost, but we're not going to talk about Adaboost directly. We're going to consider it briefly as a special case of the methods that we're talking about today, forward stage-wise additive modeling, and it's more broadly applicable gradient boosting. And gradient boosting is, I'm excited that we're getting to cover this technique because it's one of the state-of-the-art techniques used today in practice and in the competitive machine learning world of Kaggle and that sort of thing. It's basically gradient boosting, and neural networks generally are the leading methods. And we're going to get a good understanding of that today. So, start with an example. Suppose we're in the nonlinear regression setting. This is an illustration of some training data we might have. The input space is just one-dimensional x. The output space is this response quantitative variable y. And you can see the data, it's not going to be fit well with a line. Right? So what are our options? At this point, we have several that we can go to. If you're faced with such a data, what might you try? Sam?
Polynomial regression.
OK, polynomial regression. So this amounts to creating some new features, like squares, and then fitting a polynomial function, essentially using our linear methods. You just add a square term as a new feature. And so, so one version to generalize would be you make a lot of nonlinear transformations of x. Those are your new features. And then you fit with a linear method. All right.
Use a nonlinear method like a random forest?
Yeah, sure. Great. We could use a random forest like we discussed last week. Absolutely. There's one other thing that's kind of related that we discussed.
SVM with some kernel.
Great. We could do SVM with a square loss to make it a regression, and with some kind of a kernel, like a RBF kernel. Or more generally, we could use any kernel method. OK. Yeah, I guess when I said SVM with a square loss, that doesn't quite make sense. SVM is the hinge loss, so yeah. So some kernel method. Great. We could use a regression tree directly. Right? A regression tree we spoke about last week. All right, so those are some basic methods. Eventually, we'll talk about neural networks, and that could fit this directly as well. OK. So let's focus in on the creating new functions, creating new basis functions approach. So we could imagine creating some collection of new functions of x, for instance, the square function, and coming up with a linear combination of these transformations of x. So the term basis function what we've written here and what we're calling here basis functions is is exactly a feature function, or a feature that we've been discussing kind of this entire course. But when you take linear combinations of these things and they look like functions, it somehow feels sometimes more natural to call them basis functions. But in any case, you'll see different terms in different places in different treatments. All right. So once we've chosen these feature functions, the goal is to find the best linear combination of them. And for that, we can use any of our linear approaches. We can do regularization like lasso regression, ridge regression, square loss. We could do L1 loss. But the key point is that this collection of hypothesis space, this collection of prediction functions, once we fixed the features, the basis functions, is just a linear set. All right. It's a linear hypothesis space. So if we're restricting our hypothesis space to these linear combinations of fixed feature functions, fixed basis functions, then in the prediction functions we get are continuous valued, real valued. And for regression, that's fine. We're all set. But if we want to solve a problem that's not regression, so like classification or something, all right, well, we've spoken about that as well. We can transform our real valued score function into a class by thresholding. That's one thing we can do. Also, we spoke a few weeks ago about probabilistic modeling, right, where we had a real valued score function being transformed into the parameter for a distribution. So for Bernoulli, for like a classification, the parameter is just the probability of heads, probability of 1. And the transformation we talked about, like the logistic transformation and the kind of inverse CDF of a normal distribution transformation, different ways to map a score function that could take any real value, the output of this, to some number between 0 and 1. So we could also use it for ranking. Would be another example. So if you have a lot of results, a lot of possible results for a search query, you could evaluate the score of each one and then sort the result candidates by their score, and that could be a ranking for search. So the point is that even though it seems like this score function would only be useful for regression, you can, via various transformations, use it in classification or probabilistic modeling, multi-class classification with that multinomial logistic regression, different things. So this is a pretty widely useful hypothesis space, even though it's just real valued. So far, we've been speaking about manually coming up with these feature functions, GM, our basis functions. The way we're going to frame the topics of today is that we're going to find these feature functions automatically as part of the learning process. And sometimes this is called adaptive basis function modeling, in the sense that the basis functions, the feature functions, are chosen adaptively to the data, to the problem, rather than fixing them in advance manually. So in this setting, we introduce what we'll call a base hypothesis space, H. And this is going to consist of our potential feature functions. So it could be a huge class of functions, infinite, uncountably infinite class of functions. And from there, we will choose a finite, relatively small subset of these functions to be our basis. All right? So in that case, we will end up with still something of this form, a linear combination of feature functions, HM. But now, both VM, the coefficients, and HM, the feature functions, the basis functions, will be chosen adaptively using the training data. Okay? So we can now think of our hypothesis space as this collection of linear combinations of feature functions, where each of the feature functions is chosen itself from the base hypothesis space. So we can call the set of functions that we eventually are predicting with a combined hypothesis space, or just the hypothesis space. And it's a collection of linear combinations of some finite choice of functions from our base hypothesis space. Clear? Okay. All right, so given some data, learning is to choose both the coefficients and the functions. So how can we do that? Let's start, as we do, by thinking about empirical risk minimization. So we have some loss function, and we look at the average loss in our training data for a function f, chosen now from our combined hypothesis space. And we can explicitly call out the parameters of this objective. It's going to be the coefficients and the functions, right? And we would love to optimize over both of these. Optimizing over functions hm just raw sounds difficult. Let's assume we can parameterize this set of base hypothesis space functions, the set of feature functions. So we'll take theta to be some vector space Rb that parameterizes, that indexes the set of all possible infinitely many feature functions in our base hypothesis space. So now we're looking to optimize the theta. Each theta, I, corresponds to the choice of one of our ith feature function, our ith basis function. Yeah? OK. All right, so now this is something a little bit more comfortable because all of our parameters are either scalars or vectors. And we could imagine potentially solving this using our traditional techniques, gradient descent or something like that. Potentially. So we can, in fact, do it for certain classes of models. One example we haven't talked about yet, but we will soon, is neural networks. That would fit into this framework. It's important to note that this is more general than anything we've talked about so far, because we have this linear combination of functions that the functions themselves are being optimized over. So it's a little bit different. But what if we wanted our base hypothesis space to be something like trees? Something more complicated, something that's not obviously something we can differentiate. So that's the key piece. We can do our usual techniques like SGD or gradient descent if we can differentiate the subjective function with respect to theta. This is easily differentiable with respect to the v's. That's not the issue. Can we differentiate this thing with respect to theta? If we can, we're good to go, gradient descent. What we're talking about today, gradient boosting, gives us a technique to use when we cannot differentiate the subjective function with respect to the thetas. That's kind of the point that's the problem that gradient boosting solves for us. OK, so specific case of trees, let's just think about it for a moment. We have, can we parameterize the space of trees in some way with some finite dimensional vector Rb? What would be the issues we encounter if we try to kind of parameterize the space of trees with finite dimensional vector Rb? Well, what should B be, for one thing? B is the dimension of this vector.
Depth of the tree or size of the tree.
OK. So maybe depth of tree, size of the tree. So maybe we can think, for instance, all right, we have a fixed number of splits, right? OK, so maybe that's a way to fix things. And maybe we could have a different dimension for the split point of each of our B splits. But then we also have to select what variable we're splitting on, right? Well, that's a little awkward. Well, maybe we could get around that somehow. Or maybe let's simplify the set of trees. Let's try to get some traction here. What if we fixed in advance the variables we're splitting on at every node, right? And then we just have to record where we're splitting. But even then we have an issue. Even if we could parameterize a set of trees, we're still not going to be able to kind of do a gradient method because the output of a tree does not change continuously with any of these parameters. As you change the split point, the prediction will not be affected until it is, and when it is affected, it has a jump change, right? Because trees are piecewise constant. Anyway, so this is kind of a long-winded argument to say why you're not going to be able to find it's not easy to find a parameterization of trees of fixed dimension. First of all, even if you could on some restricted set of trees, it still is not something you can differentiate with respect to because the predictions are not continuous, much less differentiable with respect to parameter. Okay. So the gradient boosting technique we'll talk about today will apply to this setting whenever our loss function is differentiable with respect to the predictions, okay? And whenever we have a base hypothesis space, the set of potential feature functions, for which we can do regression, right? So regression trees would be a fine example of a base hypothesis space. You can do a regression for that, even though the predictions are not continuous or differentiable with respect to any parameter. That would work just fine for gradient boosting. All right. So a little overview of what's coming up. We're going to first talk about forward stage-wise additive modeling, which when it works is very nice. But in forward stage-wise additive modeling, there's an optimization problem that we only sometimes know how to solve. Right? And when we can't, we're stuck. Gradient boosting gets us past that sticking point by taking an iterative approach to solving that optimization problem. And then we'll discuss various variations on gradient boosting. Okay. So first, let's start with forward stage-wise additive modeling. The idea here is you kind of take the description of sequential ensemble methods I described fairly literally. So we start with prediction function. We're only dealing with continuous valued prediction functions. So we start with something that predicts identically 0. And then in every round, we have it's kind of an inductive description. In every round, we have a prediction function that is some linear combination of m-1 previously chosen basis functions. And then in the mth round, the objective is to choose your next function, h sub m, and the corresponding coefficient on that function that will add to this ensemble. All right, so we can write down an objective function for that. Some terminology that we're going to use now to initially just to kind of be suggestive of where we're going is that we're going to call this function hm, we're going to call that a step direction. And the coefficient we're going to call a step size. So you could think about what we're doing a little bit as an iterative optimization in function space. Remember, we had gradient descent. We picked a direction, the negative gradient, and then we took a step in that direction. And we added that product to the kind of thing that we've gotten so far. So we, in each round, are picking a function, which we'll think of as a step direction, and a step size, multiplying that step direction, which we add to our function that we had up to that point. All right. So here we can write an objective function very naturally. We're looking for the minimizer over step size and step direction of the previous prediction function plus the new piece, right? And then we look at the average loss on the full training set for that potential new function. And then we can try to optimize that over nu and h. All right. So the only question is, can we solve this optimization problem for every round? And if we can, this solves the problem. So it turns out we can for certain loss functions and certain function classes. So let's take one particular example, which is very intuitive, L2 boosting. So this is a regression problem setting. And we'll use the square loss. And so we just plug in the square loss to that objective function. And we have this objective. And we can simplify a bit if we make a simple assumption about our space of our base hypothesis space H. So remember, when we're optimizing this over H is coming from some base hypothesis space, right? A set of possible step directions. And if we assume that that hypothesis space is kind of has all if a particular function is in the hypothesis space and we rescale it, that function is still on the hypothesis space, so closed under rescaling, you'd say that. If that's the case, then you don't actually need this V, this new aspect, because you could just gets absorbed into the H. So let's drop that for simplicity. And we get this. So we've taken 2 steps here, haven't we? So we've rearranged a bit so that we group yi and fm minus 1 together. And then we've dropped the new here. And we get this. Now, study this for a second, and you see how you might interpret that objective function. Well, first, how would you interpret yi minus f sub m minus 1 xi? Well, first, what's f sub m minus 1 xi? Let's start there.
Score for current prediction.
Yeah, for the current prediction, what's the, for the current prediction function f sub m minus 1, what's the prediction on xi? All right. And then yi minus that?
Error.
It's the error or residual on the ith point. So given the prediction function we have so far, this term is the residual on the ith data point. Great. All right, so then how might you interpret this full objective function?
Fitting the residual.
Yeah, you're fitting the residuals. You're finding an H that fits the residuals as best we can with square loss. Great. So that is L2 boosting. L2 boosting is we find the function in the hypothesis space that fits best in terms of L2 loss. We look at the residual, and we fit the residual with the same hypothesis space, and we repeat.
So this is like a heavily overfitting.
So you're concerned this potentially is heavily overfitting.
That's right, because you are fitting the residual there. Noise could be.
Okay, so yes, so there's a potential for heavy overfitting. Let's come back to that. That's right. Okay. So one thing, if we sneak ahead, one thing we can do is we can go back to this framework and choose the H that fits it best, but then don't take the full step. Take nu to be like 0.1 instead of 1. And so we don't go all the way to fitting the residuals perfectly. We just take a little step in that direction. And that's the type of regularization that we'll end up using mostly. Okay, good point. Let's look at a quick example. So let's consider the base hypothesis space of regression stumps. So trees with only a single split. That's another way we regularize. We just use a very simple hypothesis space. Yeah. So here's input space is one-dimensional. Right? And we're going to have a single split. So in this case, this represents a tree, the prediction function corresponding to a tree with a single split. The split is at 5. To the left, we predict -2. To the right, we predict 7. Okay? This is just an example of what we call a regression stump, a stump for a tree with one split. So let's consider forward stage-wise additive modeling with an L2 loss over the base hypothesis space of regression stumps on some data, see what happens. So here's some data, and let's run this for a few rounds. So the first round, we start with constant prediction function at 0, right? The first round, we fit a stump, and we get that. Right? And then let's look at a few subsequent rounds. This is after 2 rounds. Each picture compares the previous round to the next round. So this is 2 and 3. Here's 3 and 4, 4 and 5, 49 and 50. Now we're overfitting, certainly. Yeah. Okay. So along the lines of capacity control to prevent overfitting, we could, for instance, after each stage, assess performance on a validation set, something like that. Or out of bag. We'll talk about that later. All right, any questions? Yeah.
Could you go back to the first, like from, yeah. So we start out with.
Start off with a prediction function constant at 0.
So how did our stump get two different? Like we fit the residual, so then we measured the residuals.
So okay. So first of all, the residual, when our prediction function is 0, the residual is the original data.
Yeah. Right.
So we take our original data, and we are in this setting. So this residual, this is just the original yi's. These are all 0. And now we have this objective function, and we basically say this amounts to taking our data and feeding it to the regression stump algorithm, and it gives us back a regression stump. And we claim it looks like this. So what's the?
Okay. I guess I just thought it would be linear, but there was that regression stump step that I missed.
Yeah.
Okay.
That's right. So we're choosing from a nonlinear hypothesis space.
Got it.
Of which our main one is trees. So that's right. Any other questions?
So we're like shopping for stumps of like how tall the vertical piece is, where that vertical piece.
That's right. Well, there's exactly 3 parameters to a regression stump. When you only have one input dimension. Where you split, and the values to the left and the values to the right of the split. That's right. There's only 3 things. Yeah.
So obviously for a linear hypothesis space, this doesn't work at all. But like, how would you categorize the set of spaces for which you'll get kind of the same behavior?
Okay. So the first comment, let's say that for a moment. The first comment is, obviously for a linear hypothesis space, this won't work at all. So why won't this work at all for a linear hypothesis space?
When you add them up, you're just getting another linear model, so you might as well just get the linear model in the first place.
Okay, so one is that when you add them up, you still get a linear model. But more to the point is that you've already fit this as well as you can with the linear model. So the residuals should have 0 correlation with the input in some sense. Okay, so and then the question is, it doesn't work for linear models. Is there some way to characterize when this will work? We typically use kind of non-parametric or nonlinear. Well, I think, why don't we just say it simply? If the final combined hypothesis space kind of is expressive enough to fit your data, then you're in good shape. In the linear case, you get no additional expressivity in the combined hypothesis space. So I think that would just be a good way to think about it. Can you, with linear combinations of your base prediction functions, come up with a function that will fit your data? Yeah. More questions? Okay. All right, so this is L2 boosting. Worked out very nicely. There's another example where forward stage-wise additive modeling works out nicely. Turns out it will give us Adaboost, which is the classic sequential ensemble method. So this is addressing a classification problem. So outcome space -1, 1, action space is reals, our score function. And we're in the margin setting, so just very quickly recall that the margin, when you make a prediction on x, y, the margin is your prediction score times the label y. And y is 1 or -1. And so if f of x and y have the same sign, that's good. And in that case, the margin will either be a negative times a negative, which is positive, or positive times positive, which is positive. So if you're doing a correct prediction, your margin is positive. And we want large margin in these models. All right, and so we described some loss functions, margin-based loss functions. We had the hinge loss and the logistic loss and the 0, 1 loss, all based on the margin. And to get Adaboost, we introduced a new loss function called the exponential loss. All right, so see, it has the right characteristic of small loss here, where we're doing things well, we're classifying correctly, positive margin, and aggressive loss over here. But do you see any potential issues with using exponential loss?
Diverges.
Yeah, it increases really quickly as the margin goes negative. All right. So I mean, visually, that's the main distinction, at least at this scale, between these loss functions. we'll revisit in a minute. So exponential loss. And it turns out you got to do some algebra to work it out, which we won't do, but it's sketched out in a note online. If we take a base hypothesis space of classifiers, but they're outputting the class labels as numerics, -1 and 1. And because of that, we can treat it also as a regression function. It's just that its values are only ever -1 and 1. And so we could plug it into a square loss. So forward stage-wise additive modeling reduces to a version of Adaboost in this case, if we use this exponential loss function. And you could derive that fairly straightforwardly. So back to the loss function. So what's happening over here with our large negative margin, these are the examples that are predicted incorrectly, right, because we're less than 0. But moreover, kind of confidently incorrect. So big margin means a large a score that's large in absolute value is a confident prediction. It should be, but we're both confident and wrong when we have a very small margin. And it puts a really heavy loss on those examples. So when might this be an issue? Yeah.
Mislabeled training data?
Yeah, so if you mislabel training data, that's a great example. If you have mislabeled training data, you know, it might be an example that's easy, and so the classifier correctly gives a big score, big positive score, say. But the actual label, it was mislabeled, is negative. And so the margin, it's negative. And it was confident, so it's going to have a really big loss. So your objective function is going to be heavily weighted by this error. Because it's a big margin, it's penalized exponentially. So what happens when you have the exponential loss is that it spends all this effort trying to correct these really bad errors, which might be, maybe they're mislabeled, or maybe, you know, sometimes there's just noise in the world, right? For two different x's, 70% of the time it's 1 and 30% of the time it's -1, and there's nothing you can do to resolve that, and you just do the best you can. You predict the one that happens more frequently. But in that case, you don't really want to spend a whole lot of effort trying to fix the incorrect examples. So this is why something like exponential loss can cause some issues. So, and in fact, it's observed in practice that Adaboost doesn't have great performance in scenarios where there's called high Bayes error rate. This is where, you know, there's just situations where even the best possible prediction function can't figure out what it is with perfect accuracy, or label noise. Right? It would be the other scenario where Adaboost is kind of empirically found to not do great. All right, so each of these was an instance of forward stage-wise additive modeling, which we wrote down very naturally just from the intuition of adding one new function at a time and always trying to minimize the same empirical risk, average loss. So FSAM works great for certain loss functions when we can solve that minimization problem, that optimization problem in each step. But we happen to find 2 examples where that works. But more generally, it's not easy to solve that optimization problem of how to take your next step. And so, for instance, logistic loss or cross entropy may not be clear if you write that down, if you can solve that over the space of trees or something like that. So the next topic is going to be a resolution of this problem for us.
What's cross-entropy loss?
Oh, sorry, I didn't mention cross-entropy loss yet. It's a bit of a generalization of just the logistic loss. I'll just briefly mention it so you know what's there. So in logistic loss, remember we're evaluating a probabilistic prediction. So I think the probability of class 1 is going to be 0.8. And the actual label is 1 or it's 0. And that corresponds to a certain log likelihood loss. And that's what we're averaging. Cross entropy allows us to have a ground truth that's itself a probability. So maybe instead of having hard class labels, we actually have soft class labels. It's a classification problem, but maybe imagine that we had a crowdsourced set of labels, right? And it's a difficult classification problem, even to do by hand. And we had 5 labelers for each example, and they don't agree. So we could take a majority vote or something like that, and that could be a hard label that we train to. Or you could say, you know what, let's try to fit the uncertainty. And you take the 5 labelers, and that gives you a distribution. It gives you maybe a 0.8 probability of this example being a class 1. And then you can try to fit that probability. You could say the target is to predict 0.8 every time we see that given input x. So cross entropy allows you to have a loss between a predicted probability distribution and an actual probability distribution. It's not used often. People call it cross entropy, but they usually just mean something like logistic loss or multinomial loss. But anyway, neural networks, they like to speak about cross entropy, even though they almost always have hard labels as opposed to distribution labels. All right, so now we're going to get into gradient boosting. Am I on?
Yes, you're good.
Okay. Good, good. All right. So now we're going to get into gradient boosting, AnyBoost, which is going to help us in this FSAM objective function in the case that we don't know how to solve that inner optimization problem. So this is our FSAM step. And the issue is that sometimes we do not know how to solve the optimization problem. So what to do? What if we try to solve this optimization problem locally, kind of in the same way that we solve all the optimization problems we have so far? We start at a point, and instead of trying to, in one step, figure out where the minimum is, what we've done so far is take a gradient and kind of look locally what's the good direction to step in, and we go a little bit in that direction, and we incrementally optimize our function. So that's kind of the idea of how we're going to approach this minimization problem. Because note that this minimization problem it's not local. It says find the best h and the best real valued function that minimizes this objective function. So this is not a local objective optimization problem. Okay. So the hard part, it's not the step size, it's the step direction. So let's think about this local approach a little bit. So here we have an objective function. We've written it back in terms of just the prediction function f. So this is the total loss on the training data. And if we wanted to kind of do a local method, it's almost like we want to do gradient descent on this function f, like in the function space, which feels complicated, but it's kind of the idea of what we want to do. But what saves us from getting really deep in a functional analysis is the fact that you can notice that even though f is a function, we only ever use the value of f at n specific points, right? So we only ever examine the function value at the training points. So what we'll do, let's reformulate this a bit for a moment, and let's write a vector f, which pulls out the evaluation of the function f at each of the n training points. Right? So now we have a column vector that has the relevant evaluations of the function f that we're going to need. And then we can write the objective function. OK, almost the same, but now we're indexing into a vector instead of evaluating a function. All right. And now this is something we can do gradient descent on, because the vector f, well, this is just a vector. And we can potentially, if L is differentiable, we can differentiate this objective function with respect to the vector f. We can find the gradient of f. Not clear exactly what that means, but we can do that. We can optimize over f here. Let's push this a few steps. So we'll write down the negative gradient direction as kind of the negative gradient with respect to this vector f, right, in terms of the partial derivatives. and we can calculate that. And just a little, if you're a little confused, you're right to be confused, because eventually what we're going to need to do, eventually we don't just want kind of an optimal prediction function just as a vector on the training points. We need a prediction function that generalizes to new points, not just the training data points. But we'll come to that. So for now, this picture kind of captures what we're doing. I pulled it from another source which uses slightly different notation, but I should be able to explain it just fine. So the domain that we're optimizing over are the predictions of our function on two training points. So f of x1, this dimension is the prediction we're going to produce on training point x1. And this dimension is the prediction we're going to produce on training point x2. So the vector f kind of splits into, is a point in this bottom plane. Is that clear? Our objective function, kind of our performance on these two training points, is going to be a value above that plane. So as a function of the predictions we're making at those 2 points, we're going to have the objective function. All right. Now, yeah?
It's not immediately clear that, I mean, this is one f, but we're looking for the right f. Another f could have a different surface.
No. So for any function f, we get two predictions. We get a prediction on x1 and a prediction on x2. Our two training examples. We have two training examples in this image.
I mean, for a given f, this holds, but
for a given f, we get a particular objective function value.
yeah.
Okay, and that corresponds to 1 point on this graph. And now, the set of all possible, for any possible, what this graph shows is the objective function value for all possible f's. You tell me I want to predict 10 on x1 and negative 7 on x2. Okay, that corresponds to a point down here. And then the graph tells us the value of the objective function, our total loss or average loss on those training points with those predictions. Is that clear?
Okay.
Yeah.
That means your number of dimensions equal the number of the samples.
That's correct. So in this image, the dimension is the training set size. That's right. We're optimizing over a space of dimension training set size. That's correct. We did that in one other situation earlier. You remember?
Coordinate the same.
The kernel.
In kernel method, exactly. Via the representer theorem, we could express the optimum as some linear combination of things in terms of the individual training points. That's right. Okay. But for now, we are evaluating, we're potentially optimizing directly over the predictions on the end training points. So the space we're optimizing over is Rn, where our training set size is n. So is the picture clear? That for any set of n predictions characterized by a vector f in Rn, we get some objective value, and then this is the graph of that objective value as a function of our predictions. All right. Well, given that, we can choose some initial set of predictions on the training points, and we can do gradient descent, assuming that this surface is differentiable, assuming the objective function is differentiable with respect to the predictions. So this is our objective function on the n-dimensional prediction vector. If that's differentiable with respect to f, then we can do this type of gradient descent. All right. So here we've written negative g for the step direction, which is the negative gradient. And these, notice that there's a kind of a partial derivative for every training item, training example. And the negative derivative, for reasons that will be clear soon, is called the pseudo-residual in this context. Okay. And one thing that you can note is that if the loss is a square loss, then this derivative, if you work it out, is exactly the residual. Right? So let's just work it out really quickly. So if the true label is y1, and our prediction is f1, and the loss is the square loss, and then the recipe is to differentiate with respect to the prediction f1, then we get, okay, so that's the derivative, but we want the negative, so that's the right step direction. Okay. Thank you. So there's a chain rule, so there's a negative on the minus f. So it's minus f. So up to scale factor, this is exactly the residual of our prediction. All right. But that's just for square loss. We can apply this for any loss. All right. So here's the idea. Here's the key idea. So this is all well and good to minimize over the space of functions that we're predicting for predictions just on the training points. But we want a function that is defined everywhere. All right? So the strategy is quite cute. All right? So every time we take a step, we get a new set of predictions on just the training points. And what we do is we find the function in our base hypothesis space that approximates those predictions as closely as possible. All right? You can think of that as a projection step. You're projecting this set of predictions into the set of predictions on the training set that you can actually attain with your hypothesis space. But I mean, how would we approximate predictions as closely as possible with a set of hypotheses? This is a lot like a regression problem. So this is the next step. Find the hypothesis in the hypothesis space that's closest in the L2 sense, let's say square loss, to the step direction that you want to go in. All right? So if we could change the function values directly at each of the training points, the optimal local changes would be in the direction minus g. Right? That's how we would change all the predictions at all the training points to optimally improve the objective. But when we go in that direction, we're going to end up at a set of predictions which may not be attainable by a function in our base hypothesis space. Right? There may be no stump that achieves exactly that step direction g. So let's find the prediction function in the base hypothesis space that comes as close as we can to that optimal step direction minus gi. One second. Is it clear? All right, questions?
So in the previous graph, shouldn't it be, the dimension shouldn't it be f1 of x1 and f2 of x2? Why is it the same function on the two dimensions?
So, okay, someone proposes an f, a function f, right? So let's suppose someone proposes x squared, right? Now, our training points are 0, 1, and 1, 2. These are our training points. So our training x's are 0 and 1, right? Okay. Let's define, for convenience, f1 is equal to f of 0, because this is training point 1, and this is training point 2. What is f of 0? Yeah, f of 1 1. Great. Okay. So j of f is equal to the performance of this same function on the two training points. So that's the loss of 1 comma f of 0 plus loss of 2 f of 1. Right? 1 is the value you're supposed to predict on example 0, and 2 is the thing we're supposed to predict on example 2. So loss of f of 0 is 0, f of 1 is 1. We're doing square loss, so that's 1 plus 1, which is 2. All right, so that's j of f. Is that clear? So that's j of a particular function, but we could also think of this as a function on the vector f, which are the evaluations of f at the 2 points, x1 and x2. Did that help anything?
Yeah.
It did help.
It was good.
Okay, great.
So f sub I is the output of some given function I, or given function f
Yes.
on training point xi.
That's correct.
So it's always the same f. The subscripts just are indexes into the outputs of those f's on all the training.
For a given function f, we'll create a vector f where the subscripts are its evaluations at each of the training points. That's right. But then when we want to optimize over the function f, that's equivalent to optimizing over the vector f, because in this objective function, we only ever look at the function at the training points. So there's that equivalence. Yeah?
So in this case, when you're optimizing over f, you're forgetting the hypothesis space.
We are absolutely forgetting the hypothesis space. Let me respond to that first. So you're absolutely right. So when we're optimizing here, there's no mention of a hypothesis space. We are just pretending that our hypothesis space is the set of all vectors, Rn, where the vector characterizes the set of predictions we make on the training data. So there's no reference to the original base hypothesis space H at this point. Go ahead.
So if that's true, isn't it obvious what f should be, which is just that f whose values are exactly yi?
Yeah, so for certain loss functions, so the point is that shouldn't it just be obvious what to plug in for fi? Why do we even need gradients? I mean, for certain loss functions such as square loss, you just take fi to be yi, and you're done. Okay. It's not the case for all loss functions, though. So some loss functions, like, remember the logistic loss? This is a margin-based loss, and it never gets to 0, right? So if your class is 1, the best loss you can do is arbitrarily close to 0, but your score would have to be infinity. So if you were to do that method for like logistic loss or something, then the optimal would have f be plus or minus infinity, which is not so great.
So what about this method is constraining your f?
So far, there's no constraint on f. But what's going to happen is that after every step, we project it back into a function that can actually, that's part of our hypothesis space.
Oh, you do that every step.
At every step. All right, let's repeat that piece and then see if there's more questions. So in every round, we start with this. We take a gradient step in Rn. So we adjust our function predictions at each of the training points kind of locally optimally using a negative gradient direction. And then we say, all right, if we actually need a function that's defined everywhere, which would be coming from our base hypothesis space. So let's find the function in that base hypothesis space that approximates the locally optimal step direction negative g as closely as possible in this sense. So we're searching for a function h in the hypothesis space, which gives us a legit function defined everywhere in X. And we ask that it try to approximate negative gi at each training point I as closely as possible in this square sense. And that will be the step we actually take. So we add h, or some multiple of h, to the function that we're building up. All right, let's go a few slides more, and we'll ponder some more. This is it for gradient boosting. There's variance, but this is the key idea. So we can stay on this as long as we need. So here's a little additional picture. So again, we're in this space of predictions on the training points, and there may be an optimal step direction, but this takes us to a set of predictions on the training points that's not achievable necessarily by just adding something from our base hypothesis space to what we have so far. So we project that step. We find the closest approximation to that step in our base hypothesis space. And that may be ending us up there. So that's the step direction we would actually add. Let's look at the full algorithm. Well, the last piece is how big a step do you take? And so one version is once you've chosen your step direction, HM, you just search for the step direction that minimizes your empirical risk. But more commonly, we think of the step size as a shrinkage parameter, as a regularization parameter. And if you took v to just be 1, that would be kind of the full gradient step. But often we'll tune that step size something like 0.1, or it's a tuning parameter. And as we'll see in a little while, kind of the smaller you make that, the better things tend to fit. It just takes more steps.
The better it tends to fit, or the better it tends to generalize? Or
oh, that's a good point. The better it tends to generalize rather than the better it tends to fit. Thank you. Thank you.
So at each step, we find a function. We add a function to our collection.
At each step, we add a function to our
That function
ensemble.
approximates the gradient of the loss.
The function that we add at each step is the best L2 approximation, the best approximation in square error to the unconstrained gradient step on the values of the predictions that our function makes on the training points. All right. All right, we can go over some examples by hand in our lab section. Or how about right now? All right, but just a quick recap of what the ingredients are for gradient boosting. We have a loss function. We need to be able to differentiate it with respect to the predictions. Usually we're differentiating with respect to the parameters of our hypothesis space, but all we need is to differentiate it with respect to the predictions. We need a hypothesis space on which we can do regression, because that's how we fit the gradient as best as we can. We choose a number of steps or some stopping criterion. And we need a way to choose the step size. So usually just kind of some fraction of the function gets added in each step. And then we're good to go. All right, so let's do an example. Binomial boost. Someone invented this at some point. But it's really just an application of gradient boosting with a particular loss function. So let's do classification with logistic loss. Here's a loss function. It's a margin loss. You can see the margin sitting there in the exponent, y times f of x. Right? It's a margin loss. And so what do we need to do gradient boosting on this? Mechanically, what's the step? You need to differentiate with respect to the prediction, exactly. So great. So for any training point, okay, for any training point xi, yi, we need the partial derivative of this loss with respect to the prediction itself, right? So if I would write it d right? Or I could have written that f sub I like we were doing before. All right, so let's write that out. You guys can help me with my differentiation. Log of 1 plus e to the negative y f of xi, y f of xi. Did I have that right? Okay, so let's differentiate. Which is 1 over that times the derivative of that. Okay, so 1 plus e to the negative, I'll just write mi for margin. We know that's the margin, right? And then the numerator, the derivative, 1 goes away, get the e again, so e to the negative mi times the derivative of that minus, and what's the yi? That's right, because we're differentiating with respect to the prediction f of xi, so we get the yi. Does that look right? Okay, great. Now there's this, we could simplify this a bit. Just make it a little, it's equivalent, but it's a little less to write. If we multiply the numerator and denominator by e to the mi, then this piece goes to 1, and then this piece goes to 1, and this piece goes to e to the mi. So that's negative yi e to the m sub I plus 1. All right? Okay. So this is the partial with respect to fxi. We want that, so we do that for each of the i's, and then we get the gradient g. And we want to go the negative gradient direction. All right? So the negative g, negative gradient, is equal to the negative of that. So it's like yi over e exponential of yi f of xi plus 1. And the vector is I is 1 to n, right? It's my shorthand for the gradient. That's our step direction. Now what? That's the unconstrained step direction. So now what? A new ingredient enters the picture.
Hypothesis space.
Hypothesis space enters the picture. Let's just write it down, H. And then what do we need to do with that hypothesis space?
Select an f which gives the closest value.
Okay, fantastic. Select, we'll call it H. Select an H in H. That
That gives the value closest to,
this G.
yeah.
Okay, so let's
Square.
Minimize the square.
minimize the square difference between the predictions of H and the okay, let me give it a try. So have an argmin over H is in the base hypothesis space of we're going to need a summation over I minus G sub I, that'll be the ith entry, minus H of what?
Of xi.
Yeah, H of xi, right. And then square, great. If we put a 1 over n there, that's like every regression problem we've done over the space H. So if we know how to do regression on the space H, this is what we do. Okay, so this gives us our step direction, and then we can take some fixed multiple of that, a tuning parameter, multiple of that, for where we go next. Okay. Great. All right. Every example goes this way. Yeah?
I have a question here. So if you do the gradient descent for that vector, eventually you just without project back to the hypothesis space, you will eventually, if you do that, you will find, give whatever criteria you have, you will find a vector that optimizes that a vector that optimizes this loss function. If you then just do once, is that better, or is that worse than this combination of H?
Okay, what I think you're proposing is, I think you're proposing the following. So rather than just take, so one step negative g, you're saying maybe, why don't we stay in this unconstrained space longer and get a really good value, not just a one-step update, but like a really good update that gets us much closer to a minimizer of this unconstrained version. And then you're suggesting, and then do the projection. Yeah, great question. I've also thought about this question. So one version is, where do you stop? So for logistic loss like this, what we said was that the optimizer is going to have the scores go to plus and minus infinity. So it's not entirely clear what the right target is.
I think that each data point will pull this function to a different direction. If you don't have one data point, you could do that. But you have n data point.
Well, it pulls, so it'll want f to be huge on the positives and hugely positive on the positive examples and hugely negative on the negative examples. And then,
I mean, this gradient only makes sense if the data point is just one data point. The function, the gradient function. Well, maybe it's just my understanding. So, because each data point, if essentially we pull the function to some direction, which is in favor of that data point.
oh, one second.
I mean,
So hold on. Let's suppose we have a function that looks like this. Okay, and then there's some training points. All right, so this is x1, x2, x3, x4. All right, so if the true label of this is positive, and this is negative, and this is positive, and this is positive, then the g, the gradient, is going to ask that this guy go up, this guy go down, this guy go up, and this guy go up. So it doesn't care what happens to the function overall. It wants the function value at this point to go up, but this example, x2, wants the value of the function at this point to go down. For logistic loss, where optimally it would be plus or minus infinity at each of these training points. Is this picture clear or clarifying? Yeah.
For the question that he asked, at every step we are updating the function f. So if we don't find the minimal square loss, the R minimum of the square loss, we won't be able to update the function. So we need to find the component of the function, like the basis function which is closest to the step direction to update our function, so that we can repeat the step that we did. Else we won't be able to do that. So at every step that square minimal loss is actually needed. Right.
At every step we need to do a projection to stay in the space. But the question is, the proposal was basically a projected gradient step type thing. So we take a small step and then we project it back. the idea is, why not take a big step where the big step takes you to a point that's very good in the unconstrained space, and then you project back. And I think the issue is that we don't really know the properties. I mean, if we're projecting a small distance, so there's some, I don't know, manifold, some surface of predictions that are achievable by our hypothesis space. And if we deviate by that a little bit, because we've taken a small step, and then we project back, we have some, the projection is kind of makes sense. Like, it's taking us to a point that we think will still be pretty good. Whereas if we kind of go really far away, it's hard to know whether when we project back that is going to make any sense. Okay. So almost all successful instances I know of gradient boosting are actually doing gradient tree boosting, where your base hypothesis space is a set of trees constrained in some way or another, by depth or by number of leaf nodes or something like that. So one common form is the number of leaf nodes, terminal nodes. So stumps would be 2 terminal nodes. So things have changed a little bit over the years. So the Hasty Tibshani-Friedman book recommends, let the number of terminal nodes be constrained to be kind of between 4 and 8. I remember earlier than that, people were often saying things like, oh, just boost with stumps. That's good enough. That's all you ever need. Boost with stumps. That's definitely not the case. Several years later, they're recommending between 4 and 8. So trees that have some that are kind of less trivial than just stumps. But these days, with like XGBoost and these sorts of things, people are making trees that are even much bigger than this. So 30, 40 leaf nodes or depths even, depending on the shape of the tree. Software packages. GBM is a very popular one that's in R. But sklearn has their version gradient boosting classifier, gradient boosting regressor. Kind of the state-of-the-art software packages these days are XGBoost and LightGBM. LightGBM is from Microsoft, both open source. So let's just look at another example to talk about the issues of how big steps, the step sizes that we should take. So here's some data. This is basically the same example, the same model that we had before where we were adding regression stumps together. So here's some data and various rounds of the fit, up to 100 steps. And in this case, we were taking a step size of 1, right? So just whatever we got back from the regression, that was the step that we took. Is it clear the connection now between step and these regression functions? So in every round, we pull one of those decision stumps out of the base hypothesis space H and add it to this. So this is what I would like to take a look at. What we're looking at is for this problem, we've now, this was run for step size 1. Now we've run it for 4 different step sizes, 1, 0.5, 0.1, and 0.05. And on the left, we have training step performance. So as you might expect, the bigger step size fits more quickly. So this is error. So lower error is better. So that is what we see, and that's what we expect. But on the right here is out of sample performance validation set. And we do see significant difference here in the curve. So we see for step size 1 is that we go down not even as far as some of the others, and then we start to overfit. Performance gets worse. Right? And as we use smaller step size, things get better. And there's kind of 2 things to note here. One is that the value of the minimum for slower step size, of course we have to run more steps, but eventually we get to better minima for smaller step size. That's demonstrated here. But maybe more importantly in practice is that it stays at the minimum longer. It's easier to find. So here it kind of hits the minimum and bounces back up, but here it stays there a little bit longer. And so the rule of thumb is that what people have found is that smaller step size is better, but you have to take more steps. And so make the step size as small as you have the patience to wait for it to converge. It's kind of the rule of thumb. All right, questions?
So in each case, it was bouncing back up, the error on the test set, right? Intuitively, is that just because we're adding more of the function and it's leading to a larger result that's causing it to bounce back up? What's the bounce back up due to?
Yeah, so generically speaking, if I were to show you this graph of performance, as we did something for more iterations, if it bounces back up, what would you suspect is happening? So let me back up one step. So in every step, we're adding a new function to our linear combination. So would you think it's fair to say that the kind of function we're getting is getting more complex? It's fitting the data better. So, the quick thing to say is that we are overfitting. And just as we saw at the very beginning with the decision stumps, if you run it long enough, it'll fit the data, in that example anyway, it'll fit the data perfectly. So you just need to know the right point to cut it so that you can use out-of-sample performance for that.
In this example, how many trading points do you have?
I don't know. I'm not sure. I guess you could count them. I think there's 400. Something. Not innumerable. But,
For the training set?
this is the training set.
The reason I asked is I'm wondering if there's any relationship between when it bounces up and the training set size.
Yes, I'm sure there's a relationship between the training set size and overfitting. Certainly, yeah. Cool. All right, let me mention a few variations of gradient boosting, and then I think we'll switch topics. Okay. So stochastic gradient boosting. This is actually a very useful thing, and it fits in very well with other things that we've discussed. So in stochastic gradient boosting, the idea is that in every round, instead of using your full training set, use a subset, a random subset of your training set. So typical, if you look at kind of the original paper on stochastic gradient boosting by Friedman, he says, I use half your data. The term is bag fraction. And so the question is, why might you want to do that? So kind of original explanations were things like to prevent overfitting. So by adding by using less data, it's harder to fit the data because you're not looking at it in some of your steps. And so that would kind of regularize by making it more difficult to fit the data. Okay. Another would just say, what's faster? You have less data to deal with. You're using half the data. You should be able to go, for a linear algorithm, twice as fast, maybe faster than linear, depending on the algorithm you're using. So there's speed reasons. So the way I like to think about it in our context is this is basically a mini batch method. So the true step direction, the true G would be if you used all your training data. And you're estimating that by using a subset of your training data. Okay, that's how we would view it with our machinery. Although, if that's how we're viewing it, these guidelines of 50% of the data set size no longer seem so sensible. Like, why would the way we were arguing about mini batch sizes is that the size of the mini batch should have nothing to do with how much training data you have. The mini batch size should have to do with maybe the complexity of how difficult is it to estimate the right step direction, basically. So I kind of open that as a direction for investigation. If you have very large training set sizes, do you really want to use 50% of your training data to choose your step? And I don't know. I guess I'd argue that it should have, at the end of the day, it shouldn't have anything to do with the size of your training set. It should have to do with your base hypothesis space. Maybe you need a certain number of training points to fit a tree of a certain size, and it should have to do with the function you're trying to fit. And anyway, that's my hypothesis. Could be fun to check out. So that was randomly selecting a subset of training data at every step. Then just as we did for random forest, people have introduced the idea of randomly sampling features or columns. And this wasn't part of the original proposal, but why not mix this idea in? And the XGBoost supports this feature, for instance, and they claim that a lot of people find it more useful even than stochastically sampling the rows, the examples. I know a Kaggle competitor, I asked him what he uses, and he says that, yeah, it sometimes helps, sometimes not. Like 20% to 100% feature subsample rate would be what he finds most useful. So, it's an extra tuning parameter that you can play with. Okay. Any questions? All right, let's take a short break. I want to change topics. Did you have a quick question?
Does anyone use like really mixed hypothesis spaces?
Mixed hypothesis spaces? What do you have in
Like
mind?
a combination of trees and non-tree methods, and picking the one amongst that whole sort of heterogeneous set.
Okay, so the question is, can you make a base hypothesis space that has various types of things like trees? I don't know what your other examples were, but other sets of prediction functions. And in every round, you'd find among each set the best fit and take the best of the best. I've never seen that.
I might imagine that like your first round, you could pick something linear, and then all subsequent rounds would be sort of taking the residuals from that.
Yeah, that's an interesting idea. So I guess you might be concerned that it's a pain for a tree-based method to fit essentially a linear trend, and so you might want to get rid of that first. You could also do that in a pre-processing step. So I haven't seen this kind of heterogeneous base hypothesis space. I've more seen kind of people fit models with different base hypothesis spaces and then ensemble them together with some combination. That's an interesting idea. Ray, you're asking why not aim for the minimizer of the unconstrained problem, right? So I don't know anyone who does that, but one thing people do is take a Newton step instead of a gradient step, a Newton step direction. So Newton step direction is it's like you find the best second order fit to your function, the kind of quadratic fit of your function at your point, and you jump straight to the minimizer of the quadratic, or the direction towards the minimizer of your quadratic is your step direction. So that's the step direction used by XGBoost and used by a few other gradient boosting algorithms. So that's one difference from what we've presented. And then gradient boosting also introduces some different regularization on the size of the tree, and they build their tree in a way that's more integrated with the objective function. One thing to note about gradient boosting as we presented it is that the regression step, the base hypothesis space piece, choosing the H that fits G as well as possible, that's like a black box regression out step. So you can take any regression algorithm you want and do gradient boosting on it. XGBoost opens up that black box, and they kind of have more, the way they build the tree depends more directly on the objective function. All right. Now you should be able to read the slides and get the hang of it.